Okay, so I think we'll get going for the next session, and Sarthak is the chair, so he'll take over. But before we do that, I just have a announcement, a rather important announcement, which I've also written up here on this side of the board. So we will be thanking the ICTS staff for all their incredible help and support at 2 p.m. before the start of the post-lunch session. And I request you all to please be present and, finish your lunch on time and be here, because it's a very small token on our side, but an important one, and your presence will make all the difference. So thank you. 2 p.m. today at least. Please be here on time. Thank you. Okay, Sarthak.
We are very pleased to have Zhenbin Yang. He will tell us about quantum channel capacity of traversable wormholes. Zhenbin, before you begin, there is some request from the technical staff here. They're saying if you could minimize your video, because we can see your video on the side and it's appearing twice, and they're wondering if
okay,
that's possible.
Okay. Let me see how should I do that.
I won't start your time until then.
Okay. Minimize. How about this?
Yeah. No, it's not.
Oh, it's not.
Sorry, you can minimize now. Okay.
Let me see. How about?
I think Zhenbin, it's okay. Yeah, just turn the video on and it's okay. You can.
I think now.
Oh, great. Yes. You're muted right now.
Hello.
Oh no, we
muted?
can hear you. Yes.
Mm-hmm.
Yes. Zhenbin, yeah, you can begin.
Yeah, I opened my iPad audio. Yeah. Okay. So should I start? No.
You can start now.
Okay. Yeah. Thank you for the invitation. It's pity I couldn't come, but yeah, I'm still glad that I can give this Zoom talk. So today I'm going to present some ongoing work with two of my students in Tsinghua University. Jinru Ru, he's a PhD student, and Jianming Zheng, he's a undergrad student finishing his last year. Okay, so the goal is to try to understand traversable wormhole, in particular, how much information can be sent through a traversable wormhole, the Gauss-Jeffreys wall traversable wormhole, more systematically. So that's what the nature of the talk. Okay, so first, let's have a quick review of the Gauss-Jeffreys wall traversable wormhole protocol. By the way, the talk is 1 hour, right?
No, it's 45 minutes.
45 minutes. Okay, great. Okay.
Plus questions.
So, okay. All right. So the Gauss-Jeffreys wall consider start with a sum of your double state and do a double chase deformation, and that allows the interior of the sum of your double state become traversable. So let's draw the Pawel diagram. So here we have a Pawel diagram of a conventional sum of your double states, and we want to deform this sum of your double states by this Gauss-Jeffreys wall double chase deformation. So this deformation, it's a couple two side by this operator O left, O right, and the coupling constant is denoted as G. So sometimes we will also write it as e to the IGV, but understand V as a double chase deformation. Okay, so what Gauss-Jeffreys wall found that if you turn the right sign of the coupling constant G, then this double chase deformation can create some negative non-energy. Therefore, if you have another particle coming in, then this particle can go through the wormhole. reach another side. So I have a phi right, and we can reach at phi left. So that's a basic protocol. So a few comments that usually would assigned to this protocol. The first comment is that the signal goes through the black hole interior slightly. So that itself is interesting. So it can potentially tell us about the interior of the black hole horizon, and potentially can also move us a little bit inside of the explore a little bit inside of the behind the black hole horizon. The second is that it gives you a geometric picture of quantum teleportation. That's a relation with quantum teleportation. Because we can view this sum of your double state as an entangled state between the two CFTs, and then this double trace deformation can be can also be simulated as a measurement on the right-hand side and do a unitary on the left-hand side. And through EI equal to EPR, we can understand the teleportation process by viewing that the particle got teleported by going through the wormhole. So that's a concept geometric picture. So and then there's a third point usually mentioned in this protocol that is special for this many-body for this traversable wormhole protocol is that this protocol works very well if the time separation t is order the scrambling time, like log n. Okay. If you're sending the particle before the scrambling time, then you find this particle is cannot transfer to the other side because it's entered the wormhole too late. But if you send particle much earlier than scrambling time, like the time separation is much bigger than scrambling time, then the back reaction of this particle effectively destroys this wormhole protocol. And this special feature that the time separation has to be order scrambling time is associated with, from the CFT perspective, is associated with the mechanism of operator size growth. So in other words, this quantum teleportation protocol is not a universal teleportation protocol, but it's a quantum many-body teleportation, where it uses the scrambling mechanism as a way to protect the information to send it through this wormhole. Okay, and this scrambling feature is also related with the fact that gravitational force is universal. In other words, any operator O left, O right, works. So you can use different type of operators, different type of local operators. This will produce the same type of gravitational interactions. And so it's not very fine-tuned by using which operator. Okay. And the last point we will not discuss is its relation with hidden presto. Black hole as mirror. Okay. So that's a brief review of the traversable wormhole protocol. And in our talk, we were trying to understand. So once you're given such a double trace deformation, what's the upper bound of the information that you can send through the black hole interior? So if you want, in other words, if you want to send in more and more information by acting more and more phi r operator, what's the upper limit? Okay, and we will also discuss the relation with scrambling. For example, we will also want to discuss this information upper bound for a non-maximum chaotic system. Okay. Are there any questions?
Yeah, my question is probably is related with your general capacity. If you send in a very highly energetic particle, won't it destroy the wormhole?
Yeah. So that's a mechanism that gives you upper bound. Yeah. Okay. Yeah. So that's a very natural idea, and actually this idea has been explored in our paper with Juan and Douglas. So, but only roughly. So. So precisely use the idea that if you want to send too much information, then it will destroy the wormhole. With Juan Douglas, we provide estimates of the upper bound of the information based on uncertainty principle. So okay, so what? So let's look at the argument a little bit. So we will study the geometry very close to the horizon. So we have x plus, x minus. And we have this double chase deformation that prepares some null energy at the x minus equal to 0. So that's give you a p minus. This is negative null energy. It's proportional to the coupling constant g, and then because of the we will work in the frame where phi r particle do not have a large relative boost, then this double chase deformation creates a null energy that scale with e to the t because of the boost. Okay. Now we're sending a right moving particle phi r, which got scattered to the left hand side. And based on the gravitational interaction, this phi r particle is got null translated with amount that we denoted as A plus. Okay. So what's the relation between A plus and P minus? They are basically proportional to each other. So locally near the horizon, we have a Shockwave scattering where the S matrix is given by this J 't Hooft scattering process. Here where we will look at P plus P minus times G Newton. And now because this P minus is all the little g times e to the t, then this gives us e to the I P minus, P plus, we denote it as A plus, where A plus is equal to G e to the t times G Newton. So that's the amount of, so you see that the near horizon scattering process effectively acts as a null translation on the phi r particle, whereas the amount of null translation is proportional to the coupling constant times G Newton times e to the t. Okay. And near the scrambling time, this quantity becomes order 1. Okay. Now, based on this mechanism, we can ask how much information can be sent through. So first of all, based on uncertainty principle, we can have a lower bound on the null energy of a single qubit, single bit of information, because you want to encode information in you want to send the information through width of order A plus. That tells you the minimum energy of information. So this delta P plus has to be bigger or equal to 1 over A plus. Okay. And the second is based on this upper bound on this total amount of null momentum you can send through in order to avoid gravitational back reaction. So no gravity back reaction. That requires that the total amount of P plus had to be less than order 1. Okay. Then, so based on this two relation, we got the maximum entropy estimate will be P plus over delta P plus. So the if you plug in G Newton e to the t, that's order the coupling constant little g. Okay. So so that's the estimate that was done in this paper. It's intuitively it matches our expectation because roughly speaking, the G, the strength of this coupling constant should provide some kind of upper bound on how much information can be sent through. And based on this estimate, we got to the same linear scaling. Okay. So the goal is of this work is to do a systematic study of this upper bound. In particular, we want to know what are the coefficients in front of the linear G dependence, and also how does this information upper bound depends on the Lyapunov exponent. Because as we discussed at the beginning, this essentially uses scrambling. So scrambling mechanism. So we expect it depends on the Lyapunov exponent. For example, if it's an integrable system, then we shouldn't expect it. The information can be transferred from by doing this simple double choice deformation. Okay. So go is to have a systematic. Using quantum, and the method we'll use were to use some QI quantity called quantum channel capacity.
Sorry, Zhenbin, to ask you to interrupt. What is little g? I missed. What,
oh
yeah,
the coupling? Okay. Yeah, the little g is a coupling constant.
Okay. Okay. Thank you.
Double. Yeah.
Thank you.
Yeah, are there further questions?
Take this mic.
Okay.
Can I ask a question?
Yeah.
When you say quantum channel capacity, do you mean the entanglement assisted one or just a quantum channel capacity?
Yeah, without entanglement assisted. Otherwise, I don't know if there's a universal formula.
Okay, thank you.
Mm-hmm. Okay.
Go ahead.
Okay, so maybe I'll first have a brief review of what I call the quantum channel capacity. In particular, it's not entangle assisted. So so in general, when we have a system A, and we act on a quantum channel that goes to a system B, we want to characterize how much information has been successfully sent through this quantum channel. And we can, there's this following LSD theorem. So basically, we first do for any initial state of A, we can purify with a reference system, we call it R. And for any quantum channel M, we can do a dilation, expand into a unitary. And so we got an invariant, trace over invariant. Then the LSD theorem tells you that the quantum channel capacity is given by a maximum of regularized coherent information. So I'll explain these letters in a minute. So first of all, this quantity called coherent information, it's nothing but the entropy difference between the your final system and the environment. Okay. And this little n represent, in general, we will consider you can have a many copy of the channels, and you can have a prepared entangled state between the different copy of the channels, and we will to prove there's a channel capacity achieve this upper bound. That's only proved in the limit where you have infinite many copies. So this regularized version of coherent information is the case when you have a little n copy of your channels, and you're allowed to send in any initial state between an and an. And we examine its a maximum over all the possible initial state in an, and taking the n goes to infinity. So that the LSD theorem tells you that this quantity provides is equal to the maximum amount of information that you can send through this original quantum channel. Okay. And you can also consider the system with only one copy of your channel, that is without introducing the replica. And that we define as defines a one-shot channel capacity that provides a lower bound in general the quantum channel, the actual channel capacity. Okay, so that's just a state of what I learned from quantum information theory book. In general, because of this taking maximization and taking n goes to infinity, the actual channel capacity is a hard task to calculate, and so we were trying to study this this quantum channel capacity for this Traversable wormhole protocol, and not like as rigorous as the quantum information theorists, but as a high-energy theorist. But luckily, the larger analysis simplifies things a little bit. Okay. So first, let's try to study this one-shot channel capacity. That's just reduced to calculate the maximum of the coherent information in the Traversable wormhole protocol. Okay. Are there any questions about this review part?
No, I think you can go ahead, Zhenbin.
Okay. Yeah. All right. So how should we view, how do I view this this wormhole, the Traversable wormhole as a quantum channel? So I would like to view this system in the following way. So we have a phi r, and we can have a, as I said, I want to maximize over all this inserting of many of the particles. So let's consider we have a bunch of particles phi I that have a entangled with a reference system R. So the way I view this as a quantum channel is that at t equal to 0, I have the whole state. So A contains the left Hilbert space and the right union the right Hilbert space. Okay, and that is entangled with a reference. And then we have a unitary which is given by this by by this double Church deformation. So this double Church deformation is a unitary acting on the left-right system, and then we'll trace out the right-hand side that leaves as a state on the left black hole. Okay, so in other words, this coherent information, I'll skip this letters, will just given by the entropy of the left black hole minus the entropy of the right black hole, which in this case, the right black hole is environment. Okay, and we want to characterize after this traversable wormhole protocol, how much information has been sent through to the left-hand side. Okay. So now we want to maximize over the initial state of this entropy difference. For that, we will first use Takayanagi formula. So we will HRT formula, generalized entropy formula, to write the entropy of the left black hole as the generalized entropy of the left entanglement wedge. And the entropy of the right black hole will be the entropy of the right entanglement wedge. So that is equal to max of the generalized entropy stream. Okay, and because this generalized entropy, the area piece of these two general entropy are the same, so that just equal to the QFT entropy on the left causal wedge minus the QFT entropy on the right causal wedge. Okay. Now, to estimate this maximum of the coherent information, we use Bekenstein bound. That was proved by Cassini, for example. We know that through the Bekenstein bound, the left and the entropy on the left is smaller than equal to the energy on the vacuum subtracted energy on the left, and similarly we have the inequality for the right entropy. But we cannot directly use these inequalities because their sign, because of this sign is opposite in order to achieve a maximum. But turns out that if we consider the case where information has been transferred to the left-hand side, in other words, the particle has most of the particle have been transferred to the left-hand side, then we want to interested in the situation that the energy of the left region is, the boost energy on the left region is bigger than the energy on the right region. And in this case, you can do a replica analysis to show that the Bekenstein bound on the right-hand side is always saturated. And that leads us to a very nice formula that the maximum of a coherent information will be upper bounded by the energy difference between the left and right black hole, which is nothing but the boost energy. Okay, and later we will show that you can also, I think I will not show you later, but you can also check that you can maximize over your initial state such that the left-hand side Bekenstein bound is also saturated. So in other words, this does not only provide an upper bound, but also a saturable, but actually the maximum. So that gives you this one-shot coherent information. Okay.
There's a question, sorry, Zhenbin.
Yeah. Mm-hmm.
Thanks. You're imagining throwing in a particle from the right, but you wanted to change the energy on the left. Can I think of this as throwing in a particle from the right, yet it's dressed to the left boundary? Is like that's how I
No, the particle is not initially not just on the left boundary, but after this double Church deformation, it's a unitary couple two sides. then this particle can transfer to the other side. So the energy on the left-hand side will increase because the wave package of the particle moves to the left-hand side. For example, if you imagine there's a wave package, then after transfer, so initially it's the most probability the particle is on the right-hand side, but after this transformation, you have a wave packet here. So most of this energy is on the left-hand side.
I feel like you have to say something about the gravitational dressing to say which energy goes up and which energy goes down. Maybe you want to say that this coupling somehow, in addition to moving the particle from the right to the left, it also swaps the dressing somehow.
Dressing.
Yeah.
Maybe, but I'm looking at the order one term. So the dressing is order G Newton.
No. I mean, the fact that you're changing the energy means that there's some dressing that changes the energy, right?
Yeah, the boundary.
Yeah, the boundary energy. Yeah.
Yeah. But here, this energy is a QFT energy. I use Bekenstein bound for match. But
Okay,
it's equal.
I
If the end
misunderstood.
it will evaluated by the ADM mass by gravitational dressing, right?
Thank you. No, I misunderstood. Thank you.
Zhenbin, can I ask a question?
Yeah.
When you act with this coupling, you could in principle change. I'm a little bit confused about what you mean by S left gen and S right gen. Do you mean before or after you act with the coupling?
Yeah, right. So this is after the channel, right? After the unitary.
Okay.
So, right.
And is it obvious, I guess, that you couldn't have a change in the area term due to back reaction? A little bit of back reaction that could compete with the QFT term?
I thought it will not change. Well, that correction will be higher order G Newton.
Okay.
Yeah. Right. Well, the picture I had is after the unitaries, you still get some of your double state where the particle just move to the left hand side a little bit. Right.
Any other questions?
Yeah. So that's
Actually,
approximation.
Yeah, please. Zhenbin, just before you go on, let me make sure. EL and ER are the QFT energies, as you said. But are they the full energy in the left and right-handed boundaries, or are you restricting to some causal wedge?
Right. So after acting on this double jet deformation, you have this. So let's just draw the geometry after you're acting on the double jet deformation. So you have a particle that is like mainly sitting here, right? So let me draw two different colors. So we have this E left in this left causal wedge and E right. Okay, then of course, by as Ahmed was emphasizing, after you do a gravitational dressing, solving the Einstein equation, then you'll find the change of the left energy will be change of the left ADM mass, which maybe we call it H left and H right. That.
It's the full ADM mass as measured on.
Yeah, the full ADM. Yeah. I will also take it, More precisely, I think here, this boost energy, I can I have in mind as expecting value of this difference of the ADM mass. Okay, sure, right.
Thank you.
Okay. But well, but this equation you can derive by doing rapid calculations, but I'm not going to do it here.
Sorry, I have a trouble understanding the setup. Can you remind me again, in the previous diagrammatic picture, like what is R, A, B, and environment correspond to in this?
Yeah, yeah, very good. So R is a reference. So unfortunately, I have two R's. So that's quite this R is a reference. So I have a reference, and the region A initially is a whole sum of your double state with particle excitation on the right. Right, and so that's A. So A left black hole union right black hole, and so the channel is nothing but doing this double chain deformation and trace out to the right hand side, right black hole. So this environment is right black hole, and the B is left black hole. So we are interested in how much entanglement left between the left black hole and the reference.
Thank you.
Okay, please go ahead, Zhenbin.
Okay, how many minutes do I have?
You have 7 minutes, Zhenbin.
7 minutes. Okay. Okay, so big. Okay, now now based on this this formula, we can so not very rigorous discussion about what will happen to actual channel capacity when you take n copies. So when you take n copies, then the boost boost energy also give you a upper bound of the information transfer of the channel capacity of the coherent information, but the boost energy is additive. So, and in particular, in this case, it can be achievable. So in other words, this analysis suggests that the actual channel capacity is also given by this maximum of the boost energy. Okay. So. Okay, so now we just want to estimate the maximum of the boost energy. So now here, I also imagine I can tune where I send in this particle. Okay. Maybe first let me just draw this boost energy. So first let's fix the time separation between the double chain deformation and the initial particle. So we want to calculate this boost energy. That's nothing but V e to the I G V for phi r. Okay. Then to evaluate this quantity in gravity, you can use Now we need to evaluate this expecting value of this boost operator, but in general it's a hard problem. But in gravity or in large M theory, you can use the scramble method to calculate it. In gravity, it's a shockwave calculation, and I will not. Maybe I should not give you detailed formulas, but basically, you can have a commutator of B with e to the double chase deformation plus V e to the, cancels the boost energy of this acting on the initial particle. And so if you're acting on this boost operator acting on this e to the IGV, and in this Squam-Brown theory approximation, you find it just acts on this double chase deformation, like a usual derivative. So this first term will give you the commutator of B IGV operator. And the second term is nothing but the initial coherent information, the entropy difference between the two sides before you do any double chase deformation. Okay. Okay. So now this first term is just the derivative of OTOC. So you got IG time derivative of OTOC plus I think I may mess up with a sign actually, because boost have the Hamiltonian is I times I dt, so there's no I, so it's just the time derivative of O talk plus this initial coherent information. But okay, so that's the final formula. Now we have this O talk is in this configuration. All left, all right, and phi r, phi r. Okay. Okay, so it's a manifestly the O talk is manifestly a real number because time reflection symmetry. Okay, so that's a that's a formula we got. That the turn in the coefficient in front of the yeah, okay. So this linear in coupling constant G terms was originally derived through this analysis using the uncertainty principle. But the new information is that the derivative of O talk in front of the G. Okay. And although I didn't show you the detail of this analysis, but this derivation was actually also valid for a general larger non-maximal chaotic system. So you got the same formula with a time derivative of O talk. Then, therefore, you get a formula that depends on the Lyapunov exponent. Okay, and in particular, if we draw this plot, okay, so if we draw the time derivative of O talk, then you find the O talk have a maximum at around scrambling time, and depends on your string depends on whether you have a maximum Lyapunov exponent or not. Okay. This quantity have different behaviors, and in particular for pure gravitational system, you get the coefficient is the largest. Okay. Now let me make some comments about the relation with operator size winding. So in the paper with Pawel and Douglas, we proposed another quantity to test the information transfer between the two sides. This basically is given by this this 2-point function, where you have this double chair deformation, phi right and phi left. Okay. Now this quantity depends on the what's so-called as a size winding. So basically, you have a operator phi r times the sum of your double slit, rho to the 1/2. You can expand it in terms of operator size, where chi I is product of gamma matrices or poly matrices, and you sum over all this I labels type of poly matrices. Then you find that this correlator is given by basically summing over S, QS, e to the IGS, where this QS is sum of the coefficient squared, where you require the size to you sum over all the size S operators, but without any absolute value. So those are complex, and it depends on this coupling constant G as a size winding. So this in the gravitational case, e to the IG times S is so-called the size winding mechanism. But our channel capacity is a different configuration, where all the phi operators are on the right-hand side. So because it's given by the derivative of O talk, this, if you work it out, is given by this size distribution, which is
Zhenbin,
PS.
Zhenbin, would you
Yeah,
be
I'm
able to
finishing in
finish
a
in
minute.
the next 2-3
Yeah.
minutes?
Okay. All right. Okay. So that's one thing. So so it will be only, yeah, it only depends on the OTOC, but not depends on like this particular size widening mechanism. Okay. And the second comment is that because we are looking at the volume entropy, the entropy difference between the left-hand side and the right-hand side. So you find that this coherent information piece actually not that sensitively depends on the possible perturbations between the during the evolution process. So, for example, you can imagine when you do this traversable wormhole, you accidentally sending some noise from the left-hand side and the right-hand side. Okay, and then if you look at the correlator, for example, this correlator, this type of correlator, then this information when coming to the other side will scatter with this noise. So that's a big effect. But when you look at this coherent information, it's only care about whether the information has coming to the other side. Doesn't care about whether it have scattered by going to the other side. So this noise does not play a huge important role during this analysis. But it does have some rule because when you're sending this noise, it effectively decreases this making this OTOC smaller because of this back reaction of the noise on the double chain deformation. But that seems so far seems the only effect we have found. But maybe there are other effects. Okay, that's it.
Thanks, Zhenbin. Any more questions?
Sorry, Zhenbin, the last part went by a little quickly. So I understood up till the point where you showed that you improved your earlier estimate by, there was the G and then there was the OTOC. And then what, so, or OTOC prime or whatever. And then, so I guess you can therefore compute the coefficients in front of the earlier estimate you had given. By precisely.
Yeah, so that's the coefficient. The coefficient is given by the OTOC.
Yeah, okay. I mean, there's the exponential part which you anyway had, and then this gives the additional coefficient in front.
The OTOC, right? The OTOC will have the exponential growth, so just like a G Newton e to the t.
Correct.
But this result is valid for longer time regime. Ft is all scrambling time.
Right. And then how did this? So so that is the maximum. So just to go back because I couldn't quite put it all together. So you had the single shot channel capacity, and then you had the multi-shot, and then there were various bounds you got for the total amount of.
Sorry, which one?
So at the very start of the talk, you had various bounds on the total channel capacity or information you could send across, and there was the single shot bound, and then there was this Q1 of n, right?
Yeah, the regular. Yeah.
And then was there a difference finally between Qn and Q1 of n, or what is the
in general,
takeaway? Yeah,
look quite different, but because that channel becomes super additive. But I think in this case, because of essentially because of large n, these two are the same.
I see. So either way, you get the same limit. Okay.
Well, because this upper bound is given by the boost energy, and the boost operator is additive.
Okay. I see. Okay, thanks a lot.
Further questions?
Here you consider this Gaussian first of all traversable wormhole, but Like for instance, there are different traversable wormhole protocols like a pico-size teleportation. And do you expect a similar kind of dependence on for this channel capacity for the other protocols as well?
You mean the size winding
Yes.
mechanism? Yeah, that's what I want to what I'm planning to say here. Like this channel capacity is independent of the size winding. It depends on the size distribution. Right, this P. Yeah. Well, this size winding was particularly for designed for calculating this, like the expecting value of the 1-point function at the lead time. Okay. And sometimes you may be confused that you have a non-maximal chaotic case, but you have perfect size winding. But I think this channel capacity show that if you calculate the channel capacity of such systems, you'll find it's not optimal.
Thank you.
Let's thank Zhenbin for joining us once again.